Like I told you last time, my name is Mike Baumforth. I'm a former student of Professor Eager's, and he's asked me to help out. Talked to you last time about stainless steels, and we got through austenitic and ferritic stainless steels. I wanted to spend a few minutes today on Martensitic stainless steels. It's a smaller class of stainless steels as compared to the austenitics, especially the austenitics that we talked about last time. But I did want to spend a couple of minutes on that. And then we'll spend the rest of the class talking about nickel-based alloys and some of the welding issues that go with nickel-based alloys. I wanted to mention there's a couple of books that I got most of this information from. They'd be great resources if you're interested in these things. There's the titles of the two books on stainless steel welding metallurgy and nickel-based welding metallurgy. So to start off with Martensitic stainless steels, just some general information about the Martensitic stainless steels. The composition ranges are from about 11.5 to 14 weight% chromium. That's a little lower than some of the alloys that we talked about previously. Consequently, these alloys are a little bit cheaper than most of the austenitic and some of the ferritic alloys. There are specialty alloys with a little bit higher chromium. The carbon is higher in these alloys. It's from about 0.1 to 0.25 weight%. That's what increases the hardenability of these alloys and makes them martensitic. You've also got additions of molybdenum, vanadium, and tungsten. And the structure that you end up with is typically a martensitic structure, and a lot of times you have little islands of ferrite. I'll put this diagram up real quick, and then we'll go back to that slide. This is actually a diagram that I developed doing some research earlier in my career. If you remember the Schaeffler diagram that I showed you, this is kind of that lower region of the Schaeffler diagram where you've got martensite, 100% martensite over here and 100% ferrite over here, and then between the two you get structures that have a combination of the both. And you'll see we talked about the equivalency relationships. These are the equivalency relationships that I developed for nickel and chromium for this diagram. So it's useful if you're welding martensitic or ferritic stainless steels and you're worried about the amounts of the other phase that you might find. Some of the standard alloys that you will find in martensitic stainless steels, probably the most common is 410. That's the workhorse alloy. The 416 alloy is free machining. It's got a little more sulfur in it. 420 is a little more corrosion resistant. It's got a slightly higher chromium content. And then you've also got other specialty alloys like 422 and 440. One of the limitations on martensitic stainless steels is the service temperatures, only up to about 1200 degrees F or 650 degrees C, and that's just because you start to lose both corrosion resistance and mechanical properties above those temperatures. Some of the uses, the typical applications for martensitic stainless steels include power generation, and you can see what those components might be: blades and vanes and nozzles and valve seats and that type of thing. Anywhere where you've got you need high hardness because you need wear resistance, such as a pulp and paper mill or steel mill. Also in cutlery, a lot of fine cutlery is made from the high chromium grades of martensitic stainless steel. I mentioned some of the limitations, the service temperatures. Corrosion resistance is not as good as the higher chromium stainless steels. And because it's a higher carbon, harder steel, the weldability is not typically as good as with austenitic stainless steels. Some things to consider when you're welding on a Martensitic stainless steel alloy. It's recommended that you preheat all the time when you're welding Martensitic alloys. It's not absolutely required if you've got a low carbon below about 0.1 weight percent carbon. The preheat that's recommended is about 400 to 600 degrees F. The reason for the preheat is it's like I said before, it's a Martensitic alloy. You've got to worry about hydrogen cracking, and so the preheat will help to minimize that. Post-weld heat treatment is often also used in the welding of Martensitic stainless steels. Sometimes you use an austenitic filler material, and in that case the post-weld heat treatment is not required. But if you've used a matching or other filler material and you've got a high stress type weldment, then post-weld heat treatment is a good idea to stress relieve and to temper the structure. Okay.
So if you can wait till tomorrow. It actually, there's three things that preheat does, but one of them is prevent or temper the martensite. At these temperatures, you're tempering the martensite.
Okay. Well, I'll let him answer you tomorrow then. Some other things to consider are which consumable you might use. The austenitic filler metals have a lower strength and good ductility, and so they might reduce the stresses in your weld zone. The concern that you have there is they're not as strong, and so if the reason that you're using the Martensitic stainless steel is because you're worried about strength, then you need to use a matching filler metal or something close. With that, then you will need to do a post-weld stress relief treatment. Also, just for the hydrogen issues, and it sounds like Professor Eagle will touch on that even more tomorrow, but low hydrogen practice when you're welding these, which includes cleanliness, it includes using gases that are clean and low hydrogen. It uses filler materials that are low hydrogen. That's all mandatory when you're welding on Martensitic alloys. So just continuing along the lines of weldability of the Martensitic alloys, as far as cracking goes, solidification cracking susceptibility is generally low in these alloys, but the main concern as far as cracking is the hydrogen-induced cracking, particularly for the higher carbon grades. Also, just because of the Martensitic structure, poor mechanical properties as welded. You've got low ductility, low toughness. The problem with low ductility and low toughness is you can then have catastrophic brittle failure of your component. And so you typically need to do some post-weld stress relief to reduce that. Also, there's something called reheat cracking, which is basically after the structure has been welded, the post-weld aging or reheating of the alloy can promote some carbide precipitation along grain boundaries and within the grains of the alloy, which stresses the alloy and can lead to further cracking. So that is pretty much what I wanted to cover for the Martensitic stainless steel alloys. So we'll switch gears a little bit and move over to the nickel-based alloys. So there's the title slide. Let me get So first of all, some of the standard alloys, standard nickel-based alloys, just mention what they are and give you some of the names. Nickel 200 is a 99.5% pure nickel. So there are more pure nickel alloys.
Sorry, just in the previous slide for a second.
Uh-huh.
You said low ductility and low toughness. Does one kind of apply to the other?
Well, metallurgically, they're different terms. As far as effects, they're similar, but toughness has to do with the amount of energy that something can absorb. Ductility basically has to do with when it's coming apart, the type of fracture that you get. I guess it does have to do with the amount of energy as well that it takes to come apart. But
Ductility is measured usually in elongation stretch. Ductility is a measure at slow strain rates, and impact or energy absorbed. Toughness is often referred to at high strain rates, higher strain rates, impact energies. Hitting it with a hammer. Some things that are plenty ductile with low temp. Silly putty is a good example. I can take silly putty and I can stretch it, stretch it, stretch it. Good ductility. If I pull it really quick, it snaps. That's low toughness. So there is a difference, but many people equate them. Okay, but there is a difference.
I like the silly putty example. That's a good one. So the standard nickel-based alloys, there's something called Monel, which is a nickel copper alloy, nickel 400. There's two main types of nickel-based alloys that we'll be discussing. First is solid solution strengthened alloys. These are strengthened by the alloying elements that are in them, because of the different size of the different atoms in the solid solution. It puts stress on the lattice and actually strengthens the material. Some of those that you may hear of are Inconel alloys, 600 and 625 or 690. They used to be called Inconel. Now the patents have run out and they're just called Alloy 600 and Alloy 625, etc. Some of the other ones are Hastelloy X, Haynes 230, RA 336, or just some names of these solid solution strengthened alloys. The next main group is the precipitation strengthened alloys, which includes alloy 718, 713C. There's alloys called Rene alloys. There's a Rene 41. There's Waspaloy alloys. These are all strengthened by precipitates that form during the heat treatment of the alloy. And these are called super alloys because of the high strength that can be achieved and the high heat and corrosion resistance that they can withstand. Some other ones which we really won't cover much, but there's low expansion alloys which contain cobalt. There's solid solution iron-based alloys which still have 30 to 35% nickel, but they have more iron, and so they're considered an iron-based alloy. Those are Incolloy alloys. And then there are precipitation hardenable iron-based alloys as well, such as Incolloy 925 and A286 might be some that you would hear of. Just spend a few minutes on applications of nickel-based alloys. The main reasons or applications for nickel-based alloys have to do with they have a great combination of strength and corrosion resistance, often at high temperatures. And they also are extremely highly resistant to stress corrosion, cracking, and pitting. So some of the places where these alloys typically get used are in heat treatment equipment, in heating elements, turbine engines, both rotating and static components are often made of the Inconel alloys. Chemical plants, pulp and paper mills often use the solid solution strength in alloys. High temperature waste incinerators and scrubbers are used for EPA requirements for cleaning the air from power plants and other things.
What's pitting?
Pitting is a corrosion process where small little pits are created in an alloy. Certain alloys, certain of the stainless steel alloys are susceptible to that. Austenitic stainless steel alloys are susceptible to both stress corrosion cracking and pitting in chloride environments. But the nickel-based alloys are resistant to that. Stress corrosion cracking. Have you talked about that, or will you talk about that?
No, I do it during the corrosion module at some point, but I haven't really talked a lot about stress corrosion. Certainly not in this version.
Okay. Stress corrosion cracking is just it's a form of cracking that can happen mainly in stainless steels, where you've got an environment that is corrosive. You've got a stress, and what's the third thing? A susceptible microstructure.
Actually,
And
we did sort of talk
yeah.
about it. Sort of yesterday. It's always good to.
Yeah, go ahead.
Yesterday I drew a Venn diagram. Okay. For hydrogen. Wasn't that the that was stress corrosion cracking, yes. But you have to have a stress, a microstructure, and a corrodant
Environment.
or an environment, as Mike says. And if you get all three of them, well, in hydrogen embrittlement, we have the corrodant is hydrogen, if you will. The microstructure is a hard structure like martensite. In austenitic stainless steel, you have stress, you typically have chlorides, and your microstructure happens to be a particular microstructure with carbides and things like that. So in a sense, the Venn diagram on a high level is a form of stress corrosion cracking, and you can think of hydrogen embrittlement as just a subset of one form of stress corrosion cracking. I will tell you that in the scientific literature, metallurgists throw hydrogen embrittlement and stress corrosion cracking together 70% of the time. There is a difference. I don't know if I told you this year, but certainly last semester I mentioned several times. The difference is one occurs at the anode and one occurs at the cathode. Why? Because the corrodant is hydrogen, which is positively charged. In chloride cracking, it's chlorine, it's negatively charged. So you can distinguish stress corrosion cracking from hydrogen at one level, but most of the time they just throw it all together. And so in a sense, the Venn diagram I showed you yesterday, so yes, I did cover stress corrosion cracking yesterday, but only a subset of hydrogen. Okay. Sorry about that.
That's okay. That's what I was thinking of when I was talking. So nickel-based alloys are generally austenitic, which means they have a face-centered cubic microstructure. It also means that they have a very distinct solidification structure. It means they're non-magnetic. What I've got next there is the solidification path. You go from a liquid material to a liquid plus gamma, which gamma is the Greek symbol that represents austenite, and then you go to a fully austenitic structure as you solidify. A lot of times they contain eutectic constituents, which are low melting phases. As the materials solidify, they kind of grow together as fingers, and between those fingers, the last stuff to solidify is called eutectic. and it's a lower melting temperature often than the rest of the material, and we'll talk about that as we talk about solidification cracking. Already mentioned this a little bit, but the nickel-based alloys are strengthened in two different ways. They can be strengthened by solid solution strengthening, which is, like I said earlier, it's just the solution of the various alloys, whether it's nickel and copper or nickel and chromium, nickel and other things, because they form a solution together, but they're different sizes. They stress the lattice and they strengthen one another. Precipitation hardening is also a main strengthening mechanism in nickel-based alloys, and there's various precipitates that form depending on the alloy that you're using. One of the main and most common alloys or precipitates is the gamma prime alloy, which is it's a nickel and aluminum titanium precipitate. It's a strengthening precipitate. It makes these alloys very hard, and that's a face-centered cubic. That precipitate has a face-centered cubic microstructure or lattice structure. Another one is the gamma double prime, which is a nickel niobium body-centered tetragonal, is what BCT stands for. That just has to do with the way the atoms are lined up in the lattice of that precipitate. And then there's another one called eta phase, which is a nickel titanium carbide or precipitate, and that's a hexagonal close packed, which is another lattice structure that you may have heard of. Other things that form metallurgically in these alloys are various carbides of the different alloying elements that you find. You find something called Laves phase, which is often the low melting eutectic phase that you find at the grain boundaries and at the solidification boundaries. We talked a little bit about sigma phase in stainless steels. That's also found in nickel-based alloys at times. So the one thing to keep in mind about the nickel-based alloys is that they're very complex. There's a lot of things going on in these alloys. And there's various ways that can be used for controlling the properties of these alloys. One is grain size. Grain size, since these alloys are often used in high temperature applications where creep could be a problem, and I don't know if you're familiar with what creep is, but creep is basically the sliding or the slow movement of an alloy usually at a high temperature. And so if you've got less boundary area, less place for those grains to slide against one another, then that's a good thing if that's what you're worried about. Volume fraction of the precipitates that form also have a large effect on the hardness and the strength and the properties of the material. The precipitate coherency, which means the way that they line up within the lattice of the material. When you're heat treating a material and you're growing the precipitates, if you've underaged them, you haven't grown them enough, and so they're not lining up enough to strength. They're not providing enough stress in the lattice to strengthen the material. If you've overaged them, you've grown them to where they're too big and they're not providing the strength that you want. And there's something called a peak age, is which you've grown those precipitates to a certain point where you've strengthened the material to its peak strength. And so those are all things that can be controlled when you're controlling the properties of the alloy. Another thing that's often done to control creep properties is the addition of boron. And another thing to keep in mind, especially if you're welding nickel-based alloys, is most nickel-based alloys have not been developed with welding in mind. They've been developed, to cast and then machine an airplane turbine or something like that. And welding is not always was not always kept in mind as they were developed. So because of that, we do end up with some weldability issues. The three main weldability issues in nickel-based alloys are solidification cracking, heat affected zone, liquation cracking, and strain age cracking. Strain age cracking is similar to reheat cracking that I talked about a little bit with Martensitic stainless steels and also in other steels. There's also something which I'm not going to talk about that's called ductility dip cracking. If you're interested in that, you can look in the book, or you can get in touch with me and I can give you some more information on that. So solidification cracking. Before I really talk about that a lot, I wanted to talk about the various types of boundaries that are created in an austenitic steel or austenitic nickel-based alloy as the material solidifies. So what you've got here is you've got two solid regions that are coming together as the material solidifies. And so what you end up with is, remember I talked about the low melting phases that kind of partition along and are pushed along ahead of the solidification front. You've got that will be the last to solidify. You've also got solidification cells or dendrites that are growing together. And as these fronts come together, you get something called a solidification grain boundary, where the two solidification fronts come together and it forms a boundary. Within that solidification front, between the cells or dendrites, you get something called a solidification subgrain boundary. And then sometimes what happens, after the two solidification fronts have come together, that boundary is a little bit wavy or tortuous, and you get something called a migrated grain boundary, which is this boundary that is kind of straightened out or moved. And the reason it does that is to reduce the energy of that tortuous solidification grain boundary. So that was a schematic. This is a real microstructure that demonstrates some of those boundaries. So right along here, you've got the solidification grain boundary where you had two solidification fronts coming together. Within those, you've got the solidification subgrain boundaries, and then you've got a migrated grain boundary which kind of moved away from that original solidification grain boundary. And so when you're worried about solidification cracking, you're worried about these boundaries and how much stress and how much low melting phase is present along those boundaries. So back to this slide. With gamma or with austenitic solidification, the liquid film wetting is good, and so what you get, and I wanted to show you a picture of this too, actually. These are some actual fracture surfaces of some solidification cracks in nickel-based alloys. And you can see the very well-defined dendritic structure, and it almost does look like there's a liquid film over those. And so as they pulled apart, it's due to that stress and low melting phase that was along those final solidification grain boundaries. So the liquid film wetting is good, and the solid state diffusion is low, which means that you end up with those well-defined, well-developed solidification structures that I just showed you. And we've also talked about the partitioning of the impurity elements. The titanium and the niobium and the aluminum. Actually, those aren't the impurities, those are just the alloying elements. But impurities such as sulfur and phosphor are generally low in these alloys, which is a good thing. But if they are there, they can also lead to that low melting eutectic phase along the solidification grain boundaries. The problem with the eutectic phases along the grain boundaries is they melt at a much lower temperature than the bulk material, and so they remain liquid for longer as things are solidifying. So if there's a liquid phase along the grain boundary and you put some stress on it, it's going to pull apart, it's going to crack. I hope you can see this picture. What this is a solidification crack in a nickel-based alloy. And the really dark stuff here is where the crack still exists. The kind of gray stuff here is where it pulled apart as it was solidifying, but there was enough of that liquid material left to kind of fill up the crack. And so that's called crack healing in a solidification crack, is this region right here, and then you're left with some actual cracks there at the end of the crack. So what can we do? What can we do to prevent solidification cracking? A big thing is if we can try to minimize the restraint in the material. As that material is solidifying, if it's not got stresses that are then pulling it back apart, then it's not going to crack. And so we want to try and minimize that restraint as much as possible, and there's various ways to do that. One is to weld in a solution annealed condition, which means that everything has been heated up and dissolved, so all the precipitates and everything are kind of in a big solution annealed condition. What that does is it reduces the strength of the surrounding material, and so you don't have this high strength material on each side of the weld and this low strength solidification that's going on. You have a more constant lower strength material, which then will require some post-weld heat treatment after you make the weld to restore those properties that you're interested in. Another big way to minimize restraint is with joint design. You can use different joints when you're making the weld that don't solidify, that don't form stresses and residual stresses in the weld as much. There's a couple of different examples of that here. So this would just be considered a stringer bead, or just a bead along the top of a plate. That's actually a pretty good thing generally, because you can see that these would be the solidification grain boundaries. You can see that it all kind of just grows together, and if you use the right welding parameters, you don't have to worry as much about solidification cracking, as opposed to something like this, which is a deeper and narrower weld. Because the solidification fronts are growing almost parallel to one another, and as they come together, they're also solidifying and shrinking. You end up with this solidification grain boundary right down the middle that is easy to be pulled apart. When you're making what's called a fillet weld, which is between two 90-degree members, you can also control solidification cracking by the amount of material that you put in there. If you have a nice convex weld bead like this, as opposed to a concave weld bead like this, the solidification stresses will be less, and you'll end up without cracking in the case on the right. Some other ways to minimize restraint are to use multiple pass welds. Rather than putting in a whole bunch of weld material at one time, which then solidifies and has residual stresses in it, you can use a bunch of smaller welds multiple pass welds, and that will minimize your restraint. And then the last thing you can do is just to use a solidification cracking resistant material, which resistant is in quotes there because it depends on what you're welding, and it depends on the filler metal that you use. But some of these alloys here, because of the phases, well, these are actually solid solution strengthened alloys, and this is a pure nickel alloy. You get less of that. You get less of that strengthening and hardening going on in the weld, which leads to lower restraint and less solidification cracking susceptibility. So the next weldability issue that we'll be discussing is the heat affected zone. HAZ is heat affected zone liquation cracking. The heat affected zone is the region of material next to the material from the weld that was molten or was liquid. So it was not melted, but it was definitely affected by the heat of the weld. And the reason that heat affected zone cracks can occur in this case is that alloys melt over a range of temperatures. If you remember from the phase diagrams that I know Professor Eager has showed you, and I showed you some of the stainless steel phase diagrams, as the temperature drops in an alloy, you go from liquid to a liquid plus solid region, and before you get down to a completely solid region. And so in the heat affected zone, if you've got these lower melting phases along the grain boundaries, or you've just got that liquid plus solid region on the phase diagram, you can actually end up melting part of that heat affected zone. And the